Now that we know what Fourier series is, we're going to take some time to look at a special case of the Fourier series, and that is really expanding a certain function f in terms of just sine and cosine functions. Now, the special thing that you might use this is that we use it when we want to find the Fourier series of f on 0 to L. So we're not dealing with minus L to L, we're dealing from 0 to L. And in fact, it can be done. And we normally have the options of the two trigonometry functions, which is cosine or sine. So in this case, I will just tackle using the cosine function. Later, I'll tackle using the sine function. So the objective is for getting the Fourier series of f from 0 to L with just cosine terms. Now, if I were to draw the graph is something like this. It's only from 0 to L. Let's just say L is over here. So f is defined as such. How are we going to do it? Well, we're going to use the certain property that I've mentioned in a few videos back, and that is using the odd and even functions. What do we know that when we get the Fourier series of even functions? Well, basically the cosine term gets, the sine term gets eliminated, and we're just left with the a0 constant and summation the cosine terms. Well, basically that's just the procedure. We're going to extend that property of the even function and apply it to here. So extend f to a new function g such that g is an even function, i.e. g of x is equal to f of x from 0 to L and f of minus x from minus L to 0. So if I were to draw that out on the graph, it would just look something like this. And basically this whole thing is gx. There shouldn't be any surprise. It's just basically defining a new function gx, which happens to be an even function of flipping the f of x along the y-axis, because that's the property of an even function. So since gx is even, the Fourier series is given by this thing over here. There's no surprise. The bn is equal to 0, so basically the sine term gets eliminated. And the Fourier coefficients we just calculate using the basic formulas, which is given as such. Now, once we substitute the Fourier coefficient inside there, we are at liberty to change gx into f of x. So I can just change f of x here on 0 to L. Well, why can I do that? Well, you can see that if from x is from 0 to L, I'll just basically get gx is equal to fx. So that is what I've just essentially done. So we are just actually considering maybe just the positive side. So f of x on 0 to L, the Fourier series is given by this thing over here, less the sine term, that's only a cosine term, and as well as changing the Fourier coefficients, or changing the function inside the Fourier coefficients. Why? Because integrating from 0 to L, well, basically from 0 to L, gx does equal to f of x. So we can just change this to f of x. Very easy. Y'all catch that? So there really isn't any problem, any difficulty in this. Let's just look at a simple example. The function f of x is equal to 2 raised to the power of 2x, and we want to find the Fourier series from 0 to L. Basic application of formulas: find a0, a0 is equal to this thing over here. Find an equals this thing over here. We need not find bn. Well, because of bn, the sine terms get eliminated, and basically by definition, we already shown that we don't need to find bn. So this is what we have over here, and basically this is our Fourier series. So, I mean, if I were to draw the e2x function, which if my high school maths is still with me, I believe it would be something like this, right? We can get the Fourier series of this function over here. It's just that now the Fourier series, it goes from 0 to L, and it's basically just consisting of the cosine function, which is going to be something like that. Okay, as n tends towards infinity, it will converge onto the function y equals to 2x. Or does it? Because as we had the convergence of the Fourier series, we also had the convergence of the expansion of the Fourier series from 0 to L with just the sine terms. And it just follows 3 basic rules, which I would just like to quickly go through with you right now. Well, the first rule is that, well, we still need to state the condition. So f of x is piecewise continuous on 0 to L. So it's piecewise continuous on 0 to L. And then we say from x is more than 0 or less than L, paying again careful attention to the strict inequality, Fourier series convergence to function x approach from the right side, or the right hand limit of x plus the left hand limit of x. So this is our first basic rule. It's an extension of the first theorem we had about the convergence series, noticing again the strict inequality. However, what happens if we move to the endpoints? If we move to the endpoints, things change a bit. So I'll just state the rule. suppose the right-hand derivative exists for the Fourier series converges at 0 to the function applied to 0 approach from the right side, or basically we're taking the limit as we approach 0 from the right side. Okay, now why is that so? Well, basically what we're going to do is that, you see, the convergence of the Fourier series, the one that we define, is applicable for a function that is defined from minus L to L. But this time, function f is defined from 0 to L. So we're going to apply the convergence of the Fourier series to gx now. We have to apply it to gx because gx is defined from minus L to L. And then basically, if we were to take the part which is from 0 to L, we just get the convergence theorem of the Fourier series of f. So, I mean, we're just looking at the point 0. Remember, we are evaluating gx now, gx 0 plus gx, g0 minus. So this is where the graph of gx will converge to at the point 0, and evaluating, we will have gx plus is equals to the limit as h tends towards 0 from the positive side, and we apply 0 plus h. Okay, this is gonna give us basically limit as h, the limit as h approaches 0 from the positive side, gh, because we got 0 over here, and this is just gonna give us f0 plus. I hope you can see that, because h tends towards 0 to the positive side, right? So basically, this now becomes g like this. It's gonna become like this, and this is gonna be equal to this. Why? Because again, from 0 to L, the function f is equals to g. Okay, and then we just evaluate the second limit. Just evaluate the second limit as per usual. So now we are going to approach 0 from the negative side of gx. Remember, convergence theorem, we are applying it now to gx, is equals to the limit h approaches 0 from the positive side, and 0, we got a minus h, which is going to give us limit as h approaches 0 from the positive side of minus h. But this still gives us approaching g from the, the function g applied to 0 from the positive side, and it's going to give us like this, function of f of 0, or the limit as we approach 0 from the positive side. So these two are equal, so this one gives us function 0 plus, which is the same one I wrote over here. Okay, and the second rule is that suppose the left-hand limit exists, right? Fourier series converges at L to function the limit of L approach from the negative side. That you just use the same argument. Apply the convergence theorem to the function of g, and then substituting the boundaries, or substituting the points where g is equals to f, which in this case it does if we approach L from the negative side. Okay, so that is just simply it. Okay, the term for this I forgot to mention is called half range expansion.